in section 2.2, we want to build upon where we ended off in the last section, where we stopped with z sub n. Remember, z sub n was different sets of equivalence classes when you do integers modulo n. So before we get back to that, consider the following three sets here. So I have A, it's the set of all integers that are at least 10. B is the set of integers between -5 and 9 inclusive. And C is the set of integers that are less than or equal to -6. Okay. Notice every integer is in one of these three sets, not that that matters here. Okay, so the question is there a reasonable way to define addition on the sets? So what would it mean, for example, if I took set A plus set A, and I wanted the answer to be one of these three sets? Okay, so that's what I mean by I'm adding sets. Well, I mean, what would we do? Well, it would seem reasonable here. Well, in set A, you know, how do you add two sets? Well, what if we just take two elements in the set and add them together? For example, if I pick, 15 and 1,000, both of those numbers are in set A. If I add those two together, I'm at 1,015, if I remember my numbers right. And notice that's back in A. And wouldn't that be true for any two? If you pick any two integers in A and add them together, you'd be back in A. So it would make sense to say A plus A is A. That would seem reasonable to do. Okay? What about C? What if I tried to do C plus C? Well, if I picked an element in C, say, -12 and -12, both of those are in C. If I add those together, I get -24, which would be back in C. And that's true for if you pick any two elements in C and add them together, you'd be back in C. So it would make sense to do set C plus set C is set C. That would make sense. Okay, on the other hand, well, what about B? What if I wanted to say B plus B? Using the same logic I just did, well, for example, take, 8 and 9. 8 and 9 are both in B, but if you add those together, 8 plus 9 is 17, which is in A. So from that example, it would make sense to say B plus B is A. On the other hand, what if I picked, -5 and 0? -5 plus 0 is -5, which is back in B. So from that point of view, instead of calling it A, it would make sense to call it B, but which one? Okay. So we run into a problem there. Likewise, if you tried other combinations, B and C and B and A, you might not get the same thing every single time. So that seemed reasonable. That seemed reasonable. What do you do with B plus B? You could argue A or B. So it's not really working out for these sets. Let's do another example. Let's let O be the odd integers and let E be the even integers, and see if we could define some sort of addition on these sets. For example, what if I took O plus O? So if I picked any odd integer and added it to another odd integer, you get an even integer, don't you? It would make sense to say O plus O is E. And what about E plus E? If you pick any even integer and add another even integer to it, you get an even integer. Notice I can't ruin it like I did here, right? If you pick any odd plus any odd, you get an even. I can't, so here, two specific things in here were in A, and then two when you add them were in B. Notice here I'm not running into that problem. The only other possible addition is O plus E, because addition is commutative. So O plus E and E plus O would be the same thing here, the way I'm doing this. If you take an odd and you add an even to it, what do you get? You get an odd. And so notice I don't run into this problem at all. So I really could define some addition on these two sets. O plus O is E, E plus E is E, and O plus E or E plus O would also be O. So it seems like sometimes you can maybe make this work out and sometimes you can't. Okay, now where are we headed with this? I mean, you're not used to adding sets. What we want to do is the equivalence classes, the congruence classes, that we did to get the ZNs. Notice we just have them laying there. It's ZN, and we have the equivalence classes 0, 1, 2, 3, 4, ... up to n minus 1. Could we do something like this addition on those? Okay. So let's do a theorem first. So theorem 2.6 says, if the class with A equals the class with B, and the class with C equals the class of D, then the class of A plus B, no, A plus C, equals the class of B plus D, and also the class with AC is the class with BD. Okay, the proof is very short. We'll do that very quickly. Okay, so let's assume the two classes A and B are the same, and the two classes C and D are the same. So we assume the hypothesis, no problem. Well, from the previous work, if the class with A is the class with B, remember we had a theorem that said A is congruent to B mod N. And likewise for that one too, C is congruent to D mod N. We had a theorem last time. What is it? By theorem 2.3. Okay. By theorem 2.2, which we did before, we get that A plus C is B plus D mod N. We proved that. And AC is congruent to BD mod N. We did that before. Thus, by theorem 2.3, we get the class of A plus C is the class of B plus D, and the class with AC is the class with BD. Again, so we're just piecing together theorems we've already done. Right? So if two classes are the same, then their representatives are congruent mod N. No problem. But then we showed another thing. If you have A is equivalent to B mod N and C is equivalent to D mod N, A plus C is B plus D mod N, and same for the product. AC is BD mod N. But again, if two things are equivalent mod N, that means their equivalence classes are the same. If two things are equivalent mod N, their equivalence classes are the same. So there's our proof. No problem. Okay, so what is this giving me? What's the point? I'm going to leave the statement of the theorem. Okay. Right. So the way I was adding sets before with those examples I made up, with this now we can define an addition and a multiplication. I didn't do multiplication in my examples, but we can define an addition and multiplication on equivalence classes. So in Zn, right, those are our equivalence classes, modulo n, define the class with A plus the class with B to be the class of A plus B, and the class with A times the class with B to be the class AB. Now in the book they're using plus in a circle and a dot in a circle for the operations here. I'm just writing it here. After this I'm just going to put plus and dot. I think they're trying to make you realize you're adding classes together, not numbers. You're multiplying classes together, not numbers. But from the context, I mean, you ought to be able to figure out what it is. So I'm not going to put the circles around the plus and the dot. Okay? Now what is it? What is our theorem telling us here that we just proved? Why are we doing this? Because typically, what do we use for our classes in Zn? We use 0, 1, 2, dot, 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 n minus 1, right? But there's no law that says you have to use those. Okay? So, for example, suppose I'm using these, and I want to take the class with 1 plus the class with 2. Well, if I use this rule right here, I'm going to get the class with 3, right? You just add them together, 1 plus 2. Okay. But suppose, on the other hand, now it depends on what Zn is. So suppose you were using A instead of 1 here. So suppose that if the class with A and the class with 1 are the same thing, and instead of using 1, you wanted to use A. You can use any representative you want. And in the class with 2, that's the class with B. So you use B. And so if you use the rule here, your class A plus class B is the class of A plus B. So my class and your class look completely different. But what does the theorem say? If these two classes are the same, and these two classes are the same, that representative plus that representative, the class of that is the same as the class here, which means those are going to be the same. Okay? That's the whole point of this. This definition needs to be the addition needs to be well defined. And well defined in general in math means if you have more than one way to represent an object, like here, I use this representative, you use this one. I use this one, you use this one. If there's more than one way to write an object, if you do an operation on it, you have to make sure that if I use these objects and follow the rule and get an answer, and you use the same objects with a different name, if you follow the rule and get an object over here, what we get has to be the same. That's what well-defined is. Okay? So well-defined is when you have more than one way to write an object. When you perform operations like this, our answers have to be the same if we choose different representatives for the same thing. These are the same, so those are the same. And same for multiplication, right? Right, so if I change that to a multiplication, 1 times 2, I'm going to get 2, and you're going to get AB. But again, the theorem says that 1 times 2, the class of 2 is going to be the same as the class of AB. All right, so these operations make sense. In other words, you're not going to run into this problem like I had on that first example where I did B plus B is in B. See, notice I picked 2 things in B and added them and got something in B. Then I added 2 things in B and got something in A, I believe. So notice it didn't satisfy this. Okay? So that's why that one didn't work. But that wasn't the Zn, right? This is saying it works in Zn the way we've defined integers modulo n. Okay, well, let's do a quick example here. Let's construct the addition and multiplication tables for Z3. Okay. Okay. So what are the elements in Z3 look like? Remember, Z3, it's a set of the equivalence classes. So we have the class with 0, the class with 1, and the class with 2. Remember, the class with 3 is 0, is the class with 0. Okay, now typically we think of these as classes. That's why they're putting the brackets. But from here, unless there's a reason for me to do it, maybe in a proof or something, I'm just going to write them without the brackets, okay? So I'm going to put a plus. I'm not going to put the circle around it. And we're doing 0, 1, 2, 0, 1, 2. But keep in mind, I'm adding the classes together. And then we're going to do the same with multiplication. Again, I'm not going to put the brackets. Now, most of these are very easy, right? Because remember, how do you add classes together? You add the representatives together. So 0 plus 0, well, that's 0. 0 plus 1 is 1. 0 plus 2 is 2. And same thing vertically. No problem. Now, the class with 1 plus the class with 1 is the class with 2. No problem. Okay. Now, here's where we have to be careful. The class with 1 plus the class with 2, by our definition, is the class with 1 plus 2, or the class with 3. But you really want to stick with the representatives you already have. So the class with 3 is correct, technically, but we want to stick with the representatives we have. Now, which of these is the same as the class with 3? Well, that's this one. Remember, the class with 0. Remember, these are the remainders when you divide by 3. So 2 plus 1 is 3. What's the remainder when you divide 3 by 3? Right, mod 3, it's 0. And then now we have 2 plus 2. Well, the class with 2 plus the class with 2 is the class with 4. So the class with 4, but which of these is the same as the class with 4? Well, what's the remainder when you divide 4 by 3? 1. So there's the addition table. Now the multiplication table is very quick, because 0 times any of these is 0. And 1 times any of those are themselves. So that's very easy. So the only one we have to spend any time on is the 2 times 2. But 2 times 2 is 4. We just did that one. And 4, the remainder when you divide 4 by 3 is 1. So there's your multiplication and addition tables for Z3. Okay. I wanted to look at theorem 2.7. They have properties here. Theorem 2.7. Oh gosh. Yeah, there's 10 properties there. Again, look through those. You have the class of A plus B. The class of A plus the class of B is a class of B plus class of A. You have associativity. You have of addition and multiplication. You have distributive laws. The class with A times a class with 1 is a class with A. I mean, just read through those and make sure they're standard property, and you would expect them. Okay, so just make sure you look through those. Theorem 2.7. Okay, so as a last example here, this is number 3 in the homework set. It says solve the equation x squared equals the class with 1. Again, I'm perfectly happy if you leave those off the brackets. In Z8. Okay. All right, so we're working modulo 8. Frankly, on this one, I mean, we don't have any methods for solving equations in Zn. I mean, we do for real numbers, but not in Zn. This is new. So I would just, I mean, remember, there's only 8 elements in Z8. Let's just check them all. Okay, so is the 0 class squared the 1 class? No, because 0 times 0 is 0. So 0's out. What about the class with 1? Well, 1 squared is 1. Right? So again, I'm just going to write 1. That means the class with 1. What about the class with 2? 2 squared. The class with 2 squared is a class with 4, which is not the class with 1. Remember, I'm using representatives class with 0, 1, 2, 3, 4, 5, 6, 7. So each of those is a distinct class. So 2 squared is 4. 4 is not the same as 1. Okay, what about 2x is 3? The class with 3 times the class with 3 is a class with 9. But the class with 9, what's 9 mod 8? What's the remainder when you divide 9 by 8? 1. So the class with 3 is also a solution. 4, the class with 4 squared, that's a class with 16. The class with 16 is a class with 0, because it's a multiple of 8. That was 4. 5, the class with 5 squared is a class with 25. And 25, the remainder when you divide 25 by 8 is 1. So the class of 5 squared is a class with 1. 6, the class of 6 squared, that's 36. And 36 mod 8, when you divide 36 by 8, the remainder is, what, 4? So that doesn't work. That was 6. 7, the class with 7 squared is a class of 49. When you divide 49 by 8, the remainder is 1. So the class with 7 squared is 1. And, and that's it. Notice what's interesting here, as opposed to real numbers, I have a quadratic equation, right? Think of this as a constant, right? I have x squared equals a constant. You learned by the fundamental theorem of algebra, if you're solving an equation over the complex numbers, or the real numbers, there's over the complex numbers, there's exactly n solutions, right? Whatever that exponent is, 2 solutions. Over the real numbers, there's at most n solutions in the real numbers. Notice here we have a quadratic, but we got 4 solutions. But that's because we're not working in real numbers, we're working in modular arithmetic. So it's a different operation. That's why they're putting a plus circle to indicate it's a different type of operation. Because notice in the real numbers, 5 plus 3 is 8. Well, let me. Right. In the real numbers, 5 plus 4 is 9. But in mod 8, right, and this is in the real numbers. But in Z8, 5 plus 4 is 1. In fact, it's the classes, right? Right, so the operation is completely different. In the real numbers, 5 plus 4 is 9. In Z8, the class with 5 plus the class with 4 is the class with 1. Again, I'm not writing all that. I would just say 5 plus 4 is 1. Okay, so that's what section 2.2 is all about.